So in this lecture, we will generally focus on some numerical problems regarding the topics which we have studied further. So let's start with the first question. So, so for this given component, let me draw. So for this given component, there are three sections. So here, this is x1 section. This is x2 section, and this is x3 section. So this is the basically we can think of this as a component 1, component 2, component 3. So each section is subjected to some type of load. So here it is subjected to the tensile loading of 72 kilonewton. Here it is subjected to the 20 kilonewton. Here it is 116 kilonewton, and here it is 24 kilonewton. Okay, so the Young's modulus for this part, Young's modulus for this part is equal to 200 GPa. The diameter of the first component, that is this component D1, is equal to 36 millimeter. Diameter of the second component is D2 equal to 60 millimeter. Diameter of the third component is 48 millimeter. Now length of the first component, that is L1, is equal to 100 mm. Length of the second component is equal to length of the third component, that is L2 equal to L3, which is equal to 200 mm. Now we have to find out, we have to determine first thing is maximum possible stress in the given component, and the second thing we have to calculate is the change in length of the given component under some stress. So let's start for solving the problem. So for solving it, so for the section x1, we have to calculate what is the load being subjected at the section x1. So we know that for calculating the axial load, we have to calculate the summation of load on either side. So it is easy to calculate the load on the left hand side of the x1. So it is easy if you are taking the load at left hand side instead of right hand side, because only one load is there. So it will save us some time. So we can see that on left hand side of the section x1, it is a compressive load of 24 kilonewton. So we are going to write minus 24,000 Newton from left hand side of the cross section of the axle. So we can calculate the stress at the section x1 as sigma x1 is equal to px1 upon ax1. So here px1 we have already calculated. So px1 is minus 24,000 Newton. We will always take this sign convention here. We will always take this sign of the stress, whether it is positive or negative. We are going to consider the sign while calculating the stress. And ax1 is calculated by the formula, that is area of the component 1 by pi by 4 d square. So pi by 4 d1 square. So d1 square is 36 square. So after solving it, we are going to get the value of sigma x1 as minus 23.57 Newton per millimeter square. So it is compressive stress. Negative sign. This negative sign expresses that the stress nature is compressive in nature. Compressive. Now let's calculate the value of the load at x2 section. So let me erase this thing. So for calculating the for x2 section, now suppose we are taking the load at the right hand side of the x2 section, right hand side. So px2 is equal to, so here 20 kilonewton is the tensile in nature, so we are going to write plus 20 and plus 72 kilonewton, because it is also tensile in nature. So by summing up, we are going to get 92 kilonewton plus 92 kilonewton. You have to always take the sign convention from right hand side of the x2 section. Now let's calculate the stress induced at the x2 section, that is sigma x2. So sigma x2 is equal to px2 divided by ax2. So px2, the value of px2 is plus 92,000 Newton divided by pi by 4 d square, that is pi by 4. What is the value of d2? d2 is 60 millimeter square, so pi by 4 60 square. So after solving this, we are going to get the value as plus 32.53 Newton per millimeter square. So the stress nature is at x2 section is tensile in nature. Now moving to the third section. So we are going to consider the right hand side of the x3 section, because it is only one stress acting up there on right hand side. So we can write px3 is equal to plus 72,000 Newton, because it is tensile in nature. So now from right hand side, so now calculate the value of sigma x3. So sigma x3 equal to px3 upon ax3. So the value of px3 is plus 72,000 Newton divided by pi by 4. So what is the value of d3? So the value of d3 is 48 millimeter square. So 48 square. So after calculating, we are going to get the value of sigma x3 as plus 39.78 Newton per millimeter square. So it is tensile in nature. Now we have to find out the maximum possible stress. So here you can see that sigma x3 is greater than sigma x2, which is greater than sigma x1. So we can say that the maximum possible stress in this case is 39.78, that is sigma s3 is the maximum possible stress in this given component, that is 39.78 Newton per millimeter square. So we can write Newton per millimeter square as 39.78 megapascal. So this is the solution for the first question, that is what is the maximum possible stress. Now let's focus on the calculation of the change in length. Let me clear up this thing, some parts. Now let's jump into the second question of our this numerical problem for calculating the change in length of the given component. Okay, now we have to calculate the change in length. So firstly, we have to calculate the change in length one by one in this different three sections. So delta L1 is equal to, we have already calculated the relation, like the equation for the quantities which are not varying with length. So these quantities are not varying with length, any quantities are not varying with length. So we are going to use the equation P1 L1 upon A1 E. E is constant for the whole section. So here P1 we have calculated earlier is minus 24,000 Newton. So minus 24,000 Newton multiplied by length of L1, which is 100 millimeter. So it is 100 divided by the area. So area is pi by 436 square multiplied by the Young's modulus, that is 200 gigapascal. So we can write 200 into 10 power 3 for solving it faster. So so we can by P1 by A1 we know that it will be value of sigma 1 L1 upon E. So we know the value of sigma 1. So we can write directly the value of sigma 1, that is compressive in nature, which is minus 23.57. You should always remember that you have to always take the sign convention in the question while solving it. So minus 23.57 multiplied by the 100 millimeter divided by the Young's modulus, that is 200 into 10 power 3. So after calculating, we are going to get the change in length across this cross section 1 as minus 0.011785 millimeter. Now let's calculate the change in length across the section 2. So delta L2 is equal to sigma 2 upon L2 upon E. So sigma 2 value is plus 32.53 Newton millimeter square, that's megapascal, into 200 divided by 200 into 10 power 3. So after calculating, we are going to get the change in length across the section L2 as positive of 0.03253. Similarly for delta L3, we are going to get the change in length as plus 0.03978 millimeter. It is millimeter. Now the final change in length, that is the final change in length delta L, we have to take it as, suppose delta L1 plus delta L2 plus delta L3. So the change in length is minus 0.011785 plus 0.03753 plus 0.03978, so which is equal to 0.060525 millimeter. So this is the final change in length of this component. So this is the numerical problem 1 for this section. We can discuss numerical problem for in the second lecture, because it will take this lecture will become more lengthy and it will be not supposed to happen. So let me finish this thing up. So thank you, and the more numericals we are going to deal with upcoming lectures.